Hello and welcome. My name is Mr. Stabner, and this is another lesson in logarithms. In this video, I will demonstrate the various techniques needed to solve exponential and logarithmic equations. As always, you can pause the video at any time to try any of these examples to challenge yourself before I go over how to solve them. Now, in these first set of examples, I will demonstrate how the inverse relationship between exponentials and logarithms can be used to solve equations. Now, as a review, here are the exponential and logarithmic forms that we discussed in the previous video. In order to solve the exponential equation given in example 1, I will need to convert it into logarithmic form. So let's first turn 8 to the 3x power equals to 7 into its log form. We start with the log with a base of 8 at 7 equals 3x. So if we were asked to get an exact answer, all we would have to do is divide both sides by 3, and we'll have that x equals the log base 8 of 7 divided by 3. But if we just want an approximate answer, we could have turned log base 8 of 7 into a decimal, then divided that decimal by 3, and we would get approximately 0.3119 as our final answer. So in the second example, I see a natural logarithm. I see the ln of x plus 5 equals 2. So if I want to solve this equation, I need to convert it from log form into exponential form. And as we previously discussed, the base of a natural log is just the natural number e. So I would rewrite this equation as e to the second power equals x plus 5. So if I want an exact answer without decimals, I would just subtract both sides by 5, and I would have x equals e raised to the second power minus 5. Which, if we want to have an approximate answer, we could have found what e squared is, and then subtracted 5, which would give us that x is approximately 2.389. In these examples, I will demonstrate that if you have equations with two bases that are the same, one on each side, you can simply solve an equivalent equation that ignores the bases altogether. Now here are a few rules that allows us to do this. For exponential equations, as long as the bases are the same on both sides, we actually can take their powers and create an equivalent equation. The solutions we get to the equivalent equation will be the solutions for our original equation. So example 3 shows us just that. I have a base of 5 on both sides, which means I can write an equivalent equation of x plus 1 equals 2x minus 5. After doing a little bit of algebra work, subtracting x from both sides, adding 5 to both sides, we'll finish and find that x does equal 6. In example 4, initially it looks like we can't solve this using the previous method. I do not see like bases. 2 is obviously not the same number as 16. However, we're just working with exponents. So if we can change one base to look like another, it'll make our equation that much easier to solve. And 16 is just a version of 2. It's 2 times 2 times 2 times 2, or 2 to the 4th power. So this allows me to rewrite the equation as 2 to the x plus 9 power is equal to 2 to the 4th power. However, there was an x originally as a power on 16. So anything that was originally part of the power now has to multiply to the 4 that is now there. But now that I have like bases, I can set up my equivalent equation of x plus 9 equals 4 times x, which after we subtract x from both sides and divide by 3, we'll get x equals 3 for the example number 4. Now let's take a look at example 5. Example 5 is obviously a log equation, but the bases are the same. So we can start the process very similar in the way that we started the process for exponential equations. Log base 7 on one side, log base 7 on the other side allows us to write an equation of 3x plus 6 equals x squared minus 4. Now I'm going to pause for a moment for a couple of reasons. One is, at this point you can notice that we are going to have to solve a quadratic. So part of this is going to be a little bit of solving quadratics review. But also, at some point in time, we're going to have to check our answers because we are working with a log equation, and as we've discussed previously, the logarithm cannot be 0 or negative on the inside. And so once we figure out some sort of x value, we're going to have to check our answers and see if our solutions are even possible, to see if our solutions are even in our equation's domain. But we can't check an answer if we don't have one. So let's solve this quadratic. I need to get it equal to 0. So I'm going to subtract the 3x to the right side. I'm going to subtract the 6 to the right side, which the x squared remains positive, but now the 3x has become negative, and the negative 6 combines with the negative 4 to give me negative 10. Now I have my quadratic in the format I need to solve it. Easiest way to solve a quadratic is by factoring. I'm looking for factors of negative 10 that will add together to give me negative 3, which in this case is going to be x minus 5 and x plus 2. Once we have this, we see that x minus 5 is going to equal 0, or x plus 2 is going to equal 0. So we have two potential answers, 5 and negative 2, that we are now going to check to see if those values even exist in our original equation. So I'm first going to check 5. If I take 5 and I substitute it into the x for both equations, 3 times 5 plus 6 is 21. 5 squared minus 4 is 21. And so I get log base 7 of 21 equal to log base 7 of 21, which tells me that x equals 5 is 100% a correct solution. However, if I check negative 2, what you'll notice is that 3 times negative 2 plus 6 gives me a log of 0. 0 is never in the domain of a logarithm. The base doesn't matter. If you ever get a solution that when put back into your logarithm gives you a 0 or a negative, you don't have to check anymore. That is not a solution. And so in this example, only x equals 5 is our answer. In this last example, we're working with an equation that just absolutely has no way to become like bases. So we need to actually introduce logarithms into this equation so that we can use properties in algebra to solve the equation. The good news is it actually doesn't matter which log you use. You could use log base 2, log base 5, log base 20, the common log, even the natural log. As long as you put a log to both sides, the same log to both sides, we can then start working with the equations. So, naturally, I'll use the easiest one to write and the easiest one to work with, which is natural logs. So I will start writing it as this. The natural log of 2 raised to the x plus 9 power is equal to the natural log of 5 raised to the x plus 1 power. I next will be able to rewrite this using the power property of logarithms, so I can take the x plus 9 and the x plus 1 and put them into the front of both logarithms. And it really isn't anything fancy, it just ends up being x plus 9 times the natural log of 2 equals x plus 1 times the natural log of 5. Now I know you're going to be tempted to get the decimal version of the natural log of 2 and the decimal version of the natural log of 5 quickly so that you can just go straight into the algebra. I recommend highly that you wait until you're done solving for x before you work on finding an approximate value for the answer, any sort of decimals. But don't worry, I'm not going to rush through the algebra on this one. I'm going to show you step by step, including all the little bit of Algebra 1 nuggets that you need. We're going to go through first by distributing the natural logs into the parentheses, which gives me x times the natural log of 2 plus 9 times the natural log of 2 equals x times the natural log of 5 plus 1 times the natural log of 5. Just like any equation we solve, we need to get the x's on both sides of the equation to one side of the equation. So I'm going to subtract that right side x, and I will have x natural log of 2 minus x natural log of 5. And I will subtract the 9 natural log of 2 over to the right side, which gives me the natural log of 5 minus 9 times the natural log of 2. But I need to get the x by itself. I still have two x's. But good old factoring is going to help us take the x from the first natural log of 2 and that first natural log of 5, and we're going to be able to pull it out front with a good old-fashioned GCF factor. And so I'll have x times natural log of 2 minus the natural log of 5 equals the natural log of 5 minus 9 natural log of 2. So now we have x times something equals a number, because that's all the right-hand side is right now. It's just a decimal in waiting. So the exact answer would be x equals that entire right side, natural log of 5 minus 9 times the natural log of 2, divided by the natural log of 2 minus the natural log of 5. Which, if you approximate it, x is approximately 5.05. Thank you for watching. I hope you found this video on solving exponential and logarithmic equations informative, and I hope you continue to watch more videos in the future. My name is Mr. Stabner. I hope you have a wonderful day.